do on this little video is just summarise the ATA Chapter 24. You really need to read the notes to get the details, because this video is just going to give you an overview and a summary of the key points. So please make sure you read the notes thoroughly, and then you can look at this video, and then a bit later on we'll have a little quiz just to see how we're getting on. So we've got three basic systems: the primary, the auxiliary and the emergency. The two IDGs mounted on the engines, they're considered to be the primary system. We've got an APU generator, which can also provide power to the aircraft, and we've got external AC power that we use on the ground. Those two sources are the auxiliary system. And if we lose all of our AC in flight, then we have an ADG, an air-driven generator, that comes out, and that's the emergency system. On the AC side of things, the power is distributed via two main AC buses, one essential AC bus, two utility buses, and an ADG bus. On the DC side of things, the main DC system consists of two TRUs that power the main and utility DC buses. In addition to that, there are two essential TRUs that power the essential bus, the battery bus and the emergency DC buses. We'll look at the AC bus schematic very shortly. But AC bus 1 normally powers the AC essential bus through the deactivated AC essential bus transfer contactor. If power on AC bus 1 is outside of limits, the transfer contact will connect the AC essential bus to AC bus 2 automatically. In a nutshell, we will always have power to AC essential bus, pretty much under all circumstances. This function can also be manually selected. You can transfer it across to the alternate source manually. AC utility bus 1 and 2 are normally powered by their respective main buses during flight if both IDGs are online. In the event of a single IDG operation in flight, the two utility buses will be automatically shed. Load shedding, though, is bypassed when the aircraft is in a weight on wheels condition and the flaps are at 0. So on the ground, normally you'd only have, say, ground power on, or maybe the APU on. In that situation, you will have power on the utility buses, provided the flaps are at 0. The main source of DC power for the aircraft are the two TRUs, or 4 TRUs. They change the 115 volts AC to 28 volts DC. Main TRUs 1 and 2 get AC power from their respective main AC buses, and in turn supply 28 volts DC to their main DC buses and to their respective DC utility bus. In the event of a loss of output from a main TRU, activation of a cockpit switch will isolate the two utility buses and join the main DC buses to the remaining TRU. Now, it's important to note that there's nothing automatic about that. So if you lose a TRU, you will lose the DC bus on that side, the DC main bus on that side, plus the utility bus on that side, leaving you the other TRU providing its own DC main bus and its own utility bus. So what you can do is you can operate the cockpit switch, and that will cause you to lose both of your utility buses, but regain both of the DC main buses. But we'll look at the schematic in a short while. Essential TRUs 1 and 2 supply DC power to the DC essential bus. There is only one DC essential bus, just to point out, the battery bus and the emergency DC bus. If an essential TRU failed, the remaining one will provide 100% of the requirements. It takes over straight away, and it's uninterrupted. There's no manual switch selection needed. Whenever it is electrically connected, the main battery supplies power to the main battery direct bus. And when it is electrically connected, the APU battery supplies power to both the APU battery bus and the emergency DC bus. The two batteries may power the battery bus if the battery switch is selected on and there is no output from either essential TRU. Each battery has got its own battery charger that will automatically charge the battery wherever there is AC power on the buses. The essential and battery bus systems utilize solid-state contactors. If you have a weak APU battery, then you can use external power to start the APU. The APU generator would then supply AC power to the buses, and the battery charger will then recharge the battery. So here we can see our AC bus network system. So we've got the two main AC buses, the AC essential bus, the two utility buses, and the ADG bus. And our sources of power are the generators 1 and 2, the APU generator, the external power, and the ADG generator. And all those buses are connected by various contactors. So starting off with the generator line contactor, obviously we've got two of them, GLCs 1 and 2. The GLC has got three positions: the off position that's shown in the picture, the generator position, and the transfer position. So when it's in the generator position, it connects its respective generator up to the respective AC main bus. Generator tie contactor the GTC, the generator tie contactor, has got two positions. When it is de-energized, it goes to the position that's shown in the position above. The utility buses, remember, are shed in the event of a single IDG fail, unless we're in a weight on wheels and the flaps are not at 0. And down on the APU and the external power, you can see you've got an APU contactor and there's a external power contactor. In actual fact, they're physically the same as a GLC, i.e. it's got three positions: off, the APC position, which is the auxiliary power position, and the EPC position, which is the external power position. So let's take a look at the DC side of things. So DC is primarily provided by the four TRUs, TRU1, TRU2, and the two essential TRUs. If we just focus in on the TRU1 and 2 just for now, you can see that their output comes down. If we take TRU1 as an example, comes down and feeds DC bus 1, and also comes down and feeds DC utility bus number 1. And TRU2 does DC bus 2 and utility bus 2. And those utility buses are powered by a tie relay, which has got two positions. The normal position, which is in now, which is connecting up the TRU to its respective utility bus, and then there's a transfer or tie position where it will allow the TRU to feed across and feed the other offside DC main bus. So if we had a failure of TRU1 as an example, we would lose power on DC bus 1 and lose power on DC utility bus 1. TRU2 would crack on as normal and be feeding DC bus 2 and the utility bus 2. But what can happen is we can transfer it or tie it together so that the TRU can feed one TRU can feed the two main buses, but it can't do that and the utility bus at the same time. So we're going to prioritize the main bus. So when you put it to the tie position or transfer position, the tie relays go into their alternate position. So in our scenario where we've lost TRU1, okay, it would tie across, so TRU2 would now feed DC bus 1, but it would no longer be feeding utility bus 2. Again, vice versa. On the essential side of things, there are no contactors. So you can see that the two essential TRUs just feed down directly onto the essential DC bus via some diodes. So if you lose an essential TRU, no contactors operate it. The other TRU just carries on as per normal. So all the generators are monitored by a generator control unit. And it's looking for various things, which in the notes it goes through all the things it's monitoring and protecting against. And obviously, if there's a problem, it's going to trip the generator offline. And these are the sort of limits. So it's looking at frequency limits, it's at voltage limits and current limits. And the limits are in this table. So the GCU will latch the generator off when any one of those listed limits are reached. When that happens, you have to switch off the generator and switch it back on again to try and reactivate the generator. The only exception to that is if there's a under-frequency situation. If there's an under-frequency situation, the generator will trip offline at the limits shown. So for an under frequency, it's below 375 Hertz for 3.5 seconds. It trips offline, but it doesn't latch off. Once the frequency comes back within limits, it automatically comes back online. That's the only exception. All the other limits, over frequency, over and under voltage, over current, the generator will trip and it will stay off. And if you want to try and reset the generator, you have to turn it off and put it back on again. The priority of the generated sources to feed power onto a certain bus bar is basically laid out in a certain order. So the IDG basically has priority on its own bus, and if that's not working, it will seek to find power from somewhere else in this order, which we'll go through in a sec. So automatic switching circuits will transfer to an alternate source, if applicable, following the priority sequence listed below. So first of all, it's going to try and find power from its on-side IDG. If there's no power from the IDG, it will look for it somewhere else. So the first place it looks for is the APU generator. If that's not working, it will then look to the offside IDG, and if that's not working, it will look for it from external power. The way this wiring logic is, this priority logic is done is not through any sort of computer system or anything like that. It's just simply through wiring logic of the line contactors. So the GLC, the GTCs, the EPC, and the APC contactors. Okay, so let's talk through a situation then in where we lose a generator in flight and see how this priority system works. So imagine then we're flying along in flight, there's no APU running currently, we've got two IDGs online, so everything is good, happy days, and suddenly we lose, for example, generator 2. So AC bus 2, using the priority logic, is going to try and find power from somewhere else. And the first place it's going to look for it is the APU. Well, that's not running. So the next priority would be to look for it from the IDG1. Now IDG1 is working, and so potentially we can get power across from IDG1 to AC bus 2. So some contactors have to be reconfigured. Now if generator 1 is running, that means generator line contactor 1 is in the generator position and is feeding up onto AC bus 1. Generator transfer contactor 2 would be currently in the position shown in the picture, so that's not going to do us much good at the moment. And the generator line contactor 2, because the generator is offline, then the generator line contactor 2 will be in the off position right now. This is all happening virtually instantaneously, by the way. So the APU is not running, so it can't get power from there, but the IDG1 is running, so it can get power from there. So a couple of things need to happen. Firstly, GTC2 will need to go down to the alternate position, and generator line contactor 2 needs to go across to the transfer position. So now generator 1 is feeding up through GLC1 onto AC bus 1, and generator 1 is also feeding across through GTC2 and GLC2 being in the transfer position up onto AC bus 2. And so happy days. Everything's good to go. We do, though, remember at this position we're going to lose our utility buses, because you need both generators on. You need 2 generators online for that to work. But what the crew could do is actually start at this stage. They could start the APU and get the APU generator online. So the APU generator contactor will go online. Now remember the configuration of our contactors. GTC2 has actually gone down to the lower position currently, but the APU has got a higher priority. In terms, AC bus 2 would prefer to use APU because it's a higher priority in the list of priorities. So the GLC2 has to remain in the transfer position, but the GTC2 can go across to the position it's shown in the picture, which is basically de-energized actually, and now the APU can feed AC bus 2, and generator 1 can happily feed AC bus 1. Now we've got two generators back online now, so actually we would recover our utilities. So this priority system is all well and good, but what if the generator tripped off because there was some sort of problem on a bus, like a short circuit, that caused that generator to overload and then obviously get tripped off? What the last thing we want to do now is transfer a good generator feed it onto a bad bus, because then that one will overload and then we're really in trouble. So if a generator is tripped off because of a short circuit on a bus caused by an overcurrent condition, then no transfer will take place. It will just be isolated. Connecting another source to the short circuit would obviously cause the alternate source to fail as well. So in this case, you will get an amber message. AC1 to auto transfer message will appear on the ICAS, and an amber fail light will light up in the switch on the control panel. So here's our electrical panel then. So you can see then you've got a single battery master switch. You've got power for the external AC and an external DC power switch there. Then you've got your generator switches, generator 1, generator 2 and the APU in the middle, on and then an off reset position. Then you've got 2 auto transfer switches. You can have it either in the automatic auto transfer position, in which case, you know, if main AC bus 1 or a main AC bus 2 loses power, it's going to seek it from an alternate source. The priority logic is there set in concrete, you can't change that priority logic, and then it's going to seek it from another source and hopefully find one. What you can do is turn off the auto transfer function and stop it from happening, but you can't kind of override it and make it happen. So if it should auto transfer but fails to do so, like in the example where we had an overload condition and it's been inhibited, then the fail light will come on. And then you can push the button and switch the whole auto transfer system off. Down underneath that you've got an essential power switch and a DC power switch. So looking at the essential power switch, if you remember, the essential bus is normally fed from AC bus 1, but it can take power from AC bus 2, and it will do so automatically. If AC bus 1 fails, it just there's a contactor, it just shunts across and connects it to AC bus 2. You can force that to happen for whatever reason you need to by pushing the alternate button, and now you'll force it to use the alternate source. You never really want to switch off the AC essential power, so there's no off position. It's either will automatically transfer to the alternate source, or you can force it to transfer to an alternate source. The DC power, this is just the single DC power switch. You'll notice there's no switches for the TRUs, by the way. None at all. You know, they just come online when they're powered from the AC bus. You can't turn them off. The main bus tie, so the DC power switch is controlling that main bus tie, and if you put it to the closed position, if you push the switch in and close it, basically you connect TRU1, for example, to DC bus 2, and you lose the utilities. Okay, so this picture, if you remember back at the table we looked at a little earlier, where we had all the limitations, so the over frequency, under frequency, over and under voltage, and so on. Well, this picture is just showing you where that information is coming from. It's all being processed by the GCUs, but this is where the GCU is measuring this information from, like the voltage and the frequency and so on. So I'll just leave that on for a couple of seconds just for you to peruse it. So the 6 GCUs, the GCUs, and they are all the same as each other, by the way. The GCUs have 6 circuit cards. A power supply, which has 5 feeds, a voltage regulator, which maintains 115 volts at the point of regulation, an overload monitor, which sends an input to the DCU for the overload message at 35 kVA. 35 kVA is not enough to trip it, but you will get an overload message. The GCR turns the generator on and off, and the GLCR connects the generator to the buzz. So it's a generator line contactor relay to control the generator line contactor. And the BTBR overcurrent protection prevents a good generator from feeding a bad buzz. So that provides the interlock to stop all the transferring taking place when you've got an overload, or not an overload condition, a short circuit condition, an overcurrent condition. So this is a photo of JB1, junction box number 1, which is probably the most important junction boxes. It's where all those contactors that we've been talking about are housed. Those black boxes next to the junction box are the generator control units, so one for each IDG and then one for the APU, and all of them are the same, by the way. JB1 is located just at the entrance door on the left hand side as you walk up the stairs, on the left hand side on the fuselage, on the sort of at floor level. It's just there. Obviously, normally it's buried away behind all the wardrobe unit that's there. Okay, I just want to go through this diagram quickly about the external power. Now, what we have for external power is an external power monitor, which is actually physically inside JB1. Now, the external power monitor is responsible to making sure the external power is good quality before it's allowed to go on the aircraft. And if you remember from the priority list, the external power is also the last in the list of priorities for providing power. So let's just try and follow this through now. So you've got your external power monitor, and inside the external power monitor there's monitors for the frequency and the voltage and the phase rotation. And then there's an external power ready relay, an EPPR, and there's an output coming from an AND gate. So basically all of those 3 things have to be good to get an output from that AND gate to energize the EPRR. So in other words, the frequency has to be good, the voltage has to be good, and the phase rotation has to be good. If that's all good, then the EPM can energize that external power ready relay. Now if we just go down to look at where the external power plug is, you'll see there's a pin F, and there's a line coming up. Actually, the line looks like it's coming up between E and F. If you follow that line up, it goes to a circuit breaker and up to the external power switch. So to put external power on, you obviously have to switch it on. So the switch has to be in the on position. And once the switch is in the on position, that allows the power coming up to go through and out of the switch to these set of external contactors, which are basically looking to make sure there's no other generator online. So no APU on, none of the two IDGs online. If that's all good, then the power can then leave that last relay. It's coming out of pin L there, coming down into H, into the external power monitor, to the EPRR. If the EPRR is energized, because the EPM is happy with all the quality, then the power is then allowed to get routed down, and it goes down to the external power contactor, boom, 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 and the external power can now come online. Right, so let's talk about the emergency generation system, which is basically our ram air turbine, or ADG. So this provides AC power in flight in the event of a total loss of all primary and auxiliary AC power. Now there are two types of ADGs on the 604s. Both of them have a ram air turbine that turns a generator to produce 115 volts AC at 400 Hertz. Basically, the two types of generator are, well, ram air turbine, are the wet one and the dry one. The difference between the two is how the system is released, how the ADG is released. Basically, what you have is like a lock that locks the ADG in position, and when the lock is released, it basically springs out into the airflow. And it's the method of releasing that lock that's the difference between the wet and the dry ADG. The wet ADG uses a squib, like a fire bottle squib, to release the lock, and then the ADG deploys. The dry ADG uses a solenoid operated lock release. The locking mechanism itself is very similar, it's just the release mechanism. So when the ADG is deployed, it produces 115 volts, and this power is then fed onto the ADG bus, and from there it feeds onto the AC essential bus and the DC essential bus. So all the other AC loads and DC loads are lost. This ensures all essential electrical systems are powered. It can be deployed automatically in flight by the auto deploy control unit. Or there's also a manual release. To stow the ADG, we have to be on the ground, and it's stowed manually with a restow pump, a hand pump. So what we have then is an ADCU, the ADG control unit, not to be confused with the generator control unit, which is a separate thing altogether. The generator control unit is looking after the generator side of things, just like any normal GCU. The ADG control unit, his sole job in life is to decide, are we going to deploy this ADG or not? That's his mission. He makes a decision whether to deploy or not the ADG. And to do that, he asks himself the following questions. Number 1, have we lost both AC buzzes? Number 2, are we in a weight off wheels situation? Number 3, if both of those are true, okay, what was providing power 2 seconds ago? And then based on the outcome of those answers, he will then deploy or not, as the case may be, the ADG. So the ADG will deploy automatically when the following logic is detected, as monitored by the ADCU. So loss of power both main AC buzzes, the aircraft being in a weight off wheel situation, and generator 1, 2 or the APU were online 2 seconds prior to the power loss. Now the idea or the objective behind condition 3 is purely as a safety thing to prevent inadvertent deployment of the ADG. If the aircraft's on jacks and you've got power on, if you didn't have that last bit of logic, then every time you turned off power with the aircraft on jacks, the ADG would just fly out. So when the ADG deploys automatically, happy days, everything's good, and hopefully the electrical system all configures itself properly, etc., etc. But if the ADG has failed to deploy automatically, we can manually release it. The problem is, if it has failed to deploy, automatically, then what are the problems might happen? So inside the manual release handle, you'll find 3 microswitches to activate manually the control circuits that would normally otherwise be done by the ADCU or the generator control unit. So as you pull the manual release handle up, you activate these 3 microswitches. One of them provides power to activate the AC emergency transfer contactor. A second microswitch activates a DC emergency transfer contactor at the same time. And a third microswitch energizes the hydraulic pump transfer contactor with the signal provided from the GCU once the ADG frequency is greater than 380 Hz. Now we'll look into the hydraulic systems when we do ATA 29 and the electrical pumps, because there are some issues with the logic and how it works. But we'll worry about that when we do the hydraulic system. So 3 microswitches that operate when you manually pull the handle, just in case, or just to make sure really that everything gets configured properly. Really just a very quick overview of the electrical system. You do need to look in your notes to get the full Monty, the full detail of it, but hopefully that's just given you an overview and maybe answer some questions if you weren't sure of how things were working. Okay, so that's us done for the electrics now. We'll see you on the next module.